Okay, so let's talk about our first thermodynamics flowchart. So here's what's going to happen. You are going to be getting a thermo problem. And you're going to have to make a decision the first time you get the thermo problem, and you're going to have to decide one of two things. Are you dealing with a closed system, or are you dealing with an open system? That question is very easy to answer right now because you're dealing with a closed system, but you're basically asking the question, does mass cross the boundary? Okay, that's the question. If it's no, you're over here. If it's yes, you're over here. Okay, now when it's a closed system, you're gonna write the first law. You're gonna say delta KE plus delta PE plus delta U is equal to Q minus W. And you're gonna ask yourself a whole bunch of questions. You're gonna ask yourself about KE and PE. Do they go to zero? You're going to ask yourself, is it adiabatic? You're going to ask yourself the mode of work. Okay, you're going to ask yourself lots of things there. Okay, and then what we're going to do is we're going to want to try to set the state. We want to set the state. Okay, set the state. So here's what we're going to do to set the state. This is what the main purpose of of this is going to be, is to set the state. And so to set the state, the first thing we're going to look at is it a solid? Okay, if it's a solid, the only thing we can do to set the state is the incompressible substance model. Only thing we can do. Okay, done. The next thing we can look at is if it's a liquid. Okay, if it's a liquid, well, we can use the incompressible substance model if in state 1 and state 2 it's a liquid. You can use the incompressible substance model. Absolutely you can. Okay, or what we can do is we can do the liquid approximation. In the liquid approximation, remember we were saying the property is equal to the saturation property at whatever temperature that we're dealing with. That's basically liquid approximation. Or if it's water, we can use the compressed liquid table. Okay, and this means the water is going to have to be very compressed. So it should say water at high pressure. Okay, so that's what we're dealing with. Okay, now next thing here is maybe it's not a liquid, maybe it's a mixture. If it's a mixture, what are you going to do? You're going to look at quality, the quality equation, and you are going to say that the property is equal to F plus the quality times G minus F. And we're going to have to use the tables, and we're going to have to use the tables to find our values for G and values for F. Okay, either we'll know quality or we'll find quality. Okay, or the next thing we're going to do is we're going to go over here to the world of vapors. Oops, I changed the color. I was using this lovely shade of purple. Now we're going to deal with the vapor. Now what can we do if it's a vapor? Well, we can say it's a real gas. And a real gas, we're going to use the tables. This is basically going to be superheat. Okay, so things like here we're going to have water, R22, R134A, ammonia, and propane. Okay, that's what we can use there. Okay, now over here, if it's not a real gas, what we can do is, well, we can say, let's check Z. So we can do generalized compressibility. And if Z does not equal 1, we can just use that generalized compressibility chart. Okay, we can use that generalized compressibility chart. And that's pretty, I can just put a dashed line here. It's pretty close to what we have in our tables, but it's an approximation, really, because we're using that chart, that table, that figure, I should say. Generalized compressibility figure is what I should say. It's a nice way, a compact way of trying to use the tables. You should get the same values of the tables, but they're going to be a little off because we're using this chart, this figure, sorry. Or if we say that Z is equal to 1, now we're saying it's the ideal gas model. Okay? And sometimes we can just jump right here, just right past all this. We can go directly to that Z is equal to 1, the ideal gas model. Okay? And in the ideal gas model, we have a couple choices. Is it constant specific heat? Or is it variable specific heat? Okay, and constant specific heat, we are going to use U is equal to, or delta U is equal to C sub V delta T, and delta H is equal to C sub P delta T. Variable specific heat, we're going to use the tables. Ooh, what's that going on there? Okay, so I created this flowchart off the top of my head. Okay, I did it off the top of my head. You need to have this created off the top of your head, and you need to know where you are at any moment when I ask you to set the state. Okay, you need to know all the tools you can use, all the ways you can use it. You need to know all the decisions you make. And I talked about some of the decisions along these lines. You need to know these decisions. You need to make sure that you have these figured out. So if you have questions about this table, about this flow chart, we need to talk about it. My hope is that by exam 2, you can create this by memory coming into the exam, and so you can then kind of think where you are on this flow chart and then know how to set the state. If that happens, our problems are going to be easy. If it doesn't happen, all our problems are going to be difficult, because in chapter 4, the first thing we're going to do, that open system, is going to connect. After we're going to have a whole bunch of new questions here, but we're going to connect right in here. We're going to have to answer how to set the state. Okay, so I hope that's helpful. And that's where we'll end today's lecture. And I hope then you have a good rest of your week, at the start of your week, and we'll see you in class and continue talking about thermal.